Hi everyone, welcome to lecture 29 on evidence and convergence to the truth. The objectives for this video are the following. After watching, everyone should be able to, number one, explain why you should use quantity and variety of evidence to update your beliefs. Number two, explain why you should use your total evidence to update your degrees of belief. And number three, evaluate Hume's problem of induction using what we've learned about probability theory. Okay, so welcome to the last lecture video. Last time we spoke about some of the ideas that have cropped up over the course of this class and applied our work on probability theory to them. In particular, we showed how Bayes' theorem can make sense of the way in which certain evidence in the form of our observations can either falsify or corroborate hypotheses in scientific reasoning. In this video, we'll talk a little more about evidence and various characteristics that make for more compelling evidence. After that, we'll return to the biggest problem we've faced in this course, Hume's problem of induction, and see what our work on probability theory has to say about that, which is where we'll finish. So first, what makes for more compelling evidence? We're going to talk about three things: quantity of evidence, variety of evidence, and using your total evidence. We'll spell out how each of these makes for more compelling evidence through some examples, so we're going to tackle them one by one. So first, quantity of evidence. Let's suppose we're administering a certain drug and we want to know if it's safe or not in terms of liver damage. So let's suppose our hypothesis H is that there is no liver damage when the drug is administered, and that evidence E1 is there was no liver damage when this drug was administered to one patient, and that evidence E1000 is there was no liver damage when this drug was administered to 1,000 patients. Now we think it's better to test on lots of people and form an opinion about the safety of the drug on that than just testing on one person. But why? That is, why does E1000 give us more confidence in H, the hypothesis, than E1 does? So let's pause here and have a think about the question. Well, just like we talked about in the last video, since our hypothesis is that there is no liver damage when the drug is administered, then we can deduce from that when we administer the drug to one patient, it won't cause any liver damage. So the probability of E1 given H is 1. And similarly, we can deduce from the hypothesis that it won't cause any liver damage if we administer the drug to 1,000 patients either. So the probability of E1000 given H is also 1. But from probability theory, we know that the probability of H given E1 over the probability of H equals the probability of E1 given H over the probability of E1. Since the probability of E1 given H is 1, this reads the probability of H given E1 over the probability of H equals 1 over the probability of E1. And similarly, we know that the probability of H given E1000 over the probability of H equals the probability of E1000 given H over the probability of E1000. And since the probability of E1000 given H is 1, this reads the probability of H given E1000 over the probability of H equals 1 over the probability of E1000. And finally, we notice that prior to testing the drug, perhaps when we're unsure about how safe it is, the probability that one patient escapes liver damage is higher than the probability that 1,000 patients escape liver damage. We might think that the more people we test it on, the more likely it is that at least one of them is going to experience some kind of nasty liver-related side effects. So all this is to say that the probability of E1 is greater than the probability of E1000. But then, whatever our prior probabilities on E1 and E1000 are, 1 over the probability of E1 is less than 1 over the probability of E1000. And so, using what we've derived, the probability of H given E1 over the probability of H is less than the probability of H given E1000 over the probability of H. And when we interpret what that means, that is to say the hypothesis H, that the drug doesn't cause any liver damage, is better supported by the evidence we get from observing the effects of the drug on 1,000 patients, so lots of them, rather than just one. So Bayes' theorem explains why quantity of evidence matters, in this case, we are better informed about the safety of our drug if we test it on more people. So let's turn next to variety of evidence. The same sort of reasoning explains why variety of evidence is important as well. So let's suppose we administer the same drug as before, but to two different populations this time. On one hand, we administer the drug to 1,000 patients, all between 20 and 30 years old and in good health, and we observe no liver damage. Let's call this evidence EH for healthy. Let's suppose, on the other hand, that we administer the drug to 1,000 patients of all ages and in various states of health, and we observe no liver damage. And let's call this evidence EV for variety. Now, we think we are better informed about the safety of our drug if we test it on the varied population, but the question is why? So let's pause again for a quick question. So our hypothesis again is that the drug doesn't cause liver damage, and just like before, the probability of EH given H is 1, and the probability of EV given H is also 1, because if the drug doesn't cause liver damage, we would predict no liver damage in either of the healthy or the varied populations. Now, from probability theory again, we know that the probability of H given EH over the probability of H equals the probability of EH given H over the probability of EH. But since the probability of EH given H is 1, this reads the probability of H given EH over the probability of H equals 1 over the probability of EH. And similarly, we know that the probability of H given EV over the probability of H equals the probability of EV given H over the probability of EV. And since the probability of EV given H is 1, this reads the probability of H given EV over the probability of H equals 1 over the probability of EV. But the point is that if we're unsure about the safety of the drug, then our prior probability on EH, that there'd be no liver damage in a healthy population, is higher than our prior probability on EV, that there'd be no liver damage in a varied population. We'd expect it maybe to affect someone in the varied population more so than we would in the healthy population. And that is to say, probability of EH is greater than the probability of EV. And therefore 1 over probability of EH is less than 1 over probability of EV. So looking back, the probability of H given EH over the probability of H is less than the probability of H given EV over the probability of H. That is, the hypothesis is better corroborated by testing on the varied population rather than the healthy population. So this explains why using a variety of evidence is better. So we've seen why quantity and variety of evidence better informs us. Let's now turn to total evidence. And the question here is, why should you use your total evidence when you update your degrees of belief? That is, why does total evidence better inform you, or why is it better to make decisions based on more knowledge rather than less? Suppose you accidentally scratch yourself on a rusty metal pole and it pierces your skin. You suspect that there might have been tetanus-causing bacteria on the pole, and you have to choose between getting a tetanus shot or not. Suppose you hate needles and they make you uncomfortable, then getting the shot will be uncomfortable for you. Suppose also that you have the option to take the rusty pole to a lab and you can have it tested for the tetanus bacteria, easily and at no cost. The question is, do you decide whether to get the shot without testing the pole for bacteria, or should you decide after you've tested the pole for bacteria? Now, a nice way to see that you should test the pole first and then decide, that is, that you should make your decision using more knowledge rather than less, is by graphing the situation. Now, since we're unsure about whether there were tetanus-causing bacteria on the pole, we're reasoning under uncertainty here, and so we can reason using expected utilities like we did at the beginning of week 9. That is, we can draw a graph as follows. Probability from 0 to 1 is our x-axis, and utility is on the y-axis. The probability here is the probability that there was tetanus-causing bacteria on the pole, and the utility is in terms of whether we get the tetanus shot or not. so the decision we're trying to make here. Now, if the probability that there were tetanus-causing bacteria on the pole is 0, you would prefer not to get the shot than to get the shot because it's uncomfortable for you, and you wouldn't need it anyway in that case. So your utility for getting the shot is lower than your utility for not getting the shot. So let's represent the expected utility of getting the shot as this red line, and the expected utility of not getting the shot as this blue line. On the other hand, if the probability that there were tetanus-causing bacteria on the pole is 1, then you would much prefer to get the shot than to not get it because of the danger the tetanus would pose to your health. So the expected utility of getting the shot when the probability is 1 is higher than the expected utility of not getting the shot when the probability is 1. Now, since expected utility is an average, these lines are straight on this graph. So here's our expected utility of getting the shot in red as a function of the probability that there is tetanus-causing bacteria on the pole. And here's our expected utility of not getting the shot in blue as a function of the probability that there is tetanus-causing bacteria on the pole. Now, we're interested in choosing whether to get the shot or not without the information we can get if we test the pole, or with the information we can get if we test the pole. Mathematically, these are quite involved to spell out, so we're going to skip over the derivations here, and instead we'll just represent it graphically, and we'll say this. Deciding which option to pursue without the extra information is called the prior Bayes act, because you act prior to learning the new information. And if we maximize expected utility according to the prior Bayes act, then we will simply choose the course of action that gives us the highest expected utility. That means you should choose the course of action corresponding to whichever line is higher on this graph at any one point. And well, if we look at the graph, we see that from here to here, that corresponds to not getting the shot, and from here to here, that corresponds to getting the shot. So this line in black here corresponds to your maximized expected utility when you choose prior to the new information. So what happens when we learn the new information and decide on the basis of that? Deciding this way is called the posterior Bayes act, and well, mathematically, if you maximize your expected utility in the light of the new information, then your expected utility looks like this dotted line I'm drawing. It's a straight line because it's an average that joins your max expected utility when the probability is 0 to the max expected utility when the probability is 1. Now, why this line corresponds to the case where you choose in light of new information isn't going to be important for us. That would take us a little bit beyond the scope of the course. But this is how you would graph the posterior Bayes act, and just knowing how you draw it on a graph like this will be all we'll need to know. So what have we got? The black solid line corresponds to the prior Bayes act when you decide on the basis of the information currently available. The dotted black line corresponds to the posterior Bayes act when you decide after you've learnt the new information. And what we can see is that the dotted line is higher than the solid black line at every point, except when the probability that the pole has tetanus is either 0 or 1, in which case they're equal. And what this tells us, interpreting this, is that you should make your decision on the basis of all the information. So you should get that pole tested and decide after you get the results if you want to maximize expected utility. If the probability that the pole has tetanus bacteria on it is 0, of course, then deciding now or after you get the pole tested results in the same expected utility, and in that case you would choose not to get the shot if you were maximizing expected utility. And if the probability that the pole has tetanus bacteria on it is 1, then deciding now or after you get the pole tested results in the same expected utility, and in that case we see that you would choose to get the shot. But the point is, for any other value of P, the probability that the pole has tetanus bacteria on it, it's strictly better for you to choose whether to get the shot or not after you have had the pole tested and got the results back. So this shows us why it's better to know something rather than nothing, or this is why it's better to make your decisions on the basis of your total evidence, everything you can gather, rather than a restricted set of information, when there is more information available. The posterior Bayes Act has a higher expected utility than the prior Bayes Act. So, if you're maximizing expected utility, you should act on the basis of your total evidence. Okay, so that rounds off our discussion of evidence. We've seen why quantity, variety, and totality of evidence are important in making decisions. To conclude the course, we're going to look back at Hume's problem and say a few things about it in light of our work on probability theory. Hume's problem, remember, in essence said this: we cannot rationally justify a system of scientific induction, so we have to admit a certain degree of skepticism about our predictions. Now, suppose we're flipping a coin and we think it's biased, but we don't know which way. Perhaps we think it's biased towards heads or it's biased towards tails. We flip the coin over and over again, and we update our degrees of belief in the chance hypotheses, just like we were talking about last week via Bayes' theorem. Now, what we said last week was that if you believe that the coin is biased in favor of heads, so that the chance the coin comes up heads, for example, might be 2/3, then as we saw, your degree of belief in the statement that the chance the coin will come up heads is 2/3 gets closer and closer to 1 in the long run. That was the weak law of large numbers. So while Hume's problem in this context says you can't reliably predict that the coin will come up heads next time, no matter what you've observed in the past, our work on probability theory shows us how we might reply. And we might say, okay, but I believe that I will learn the true chances in the long run. Knowing the true chances won't tell me for sure which side the coin will come up, of course, but we can't expect any more than this. Knowing the true chances are as good as it gets, and I believe I will learn the true chances on the basis of my observations. Now, one slight problem with this is the following. What if I was just wrong about the coin being biased? So suppose, for example, that the coin is actually fair, then no matter how many coin flips I observe, because I assign probability 0 to the statement that the coin is fair, I will never learn that it's fair on the basis of my coin flips. So if someone else believed the coin was fair, and we were both sat there flipping it, then that person's beliefs would converge on the true chances, but mine never will. Because if I believe there's a 0% chance the coin is fair, then my degree of belief in the chance that the coin is fair given any outcome will still be 0. So when I update my beliefs using Bayes' theorem, it just remains stuck at 0. So my beliefs will never converge on the true chances. But because of the way my beliefs are structured, I still believe I will learn the true chances. So this is problematic. I can't be skeptical about myself learning the true chances. I believe that will happen. But the other person can be skeptical about whether I'll learn the true chances. And so the point of this is that if we're closed-minded and we don't allow for the possibility of certain things, we assign them probability 0, then there is still room for skepticism here. And so the way to get around this problem is basically to be open-minded. You might assign, of course, a very strong probability to the statement that the coin is biased in favor of heads or tails, but you should also assign some non-zero probability to the statement that the coin is fair. You keep your mind open to that possibility. Then if everyone does that, on the basis of a very long sequence of coin flips, we all update our beliefs using the same evidence, and our beliefs will all converge to the truth, to the true chances. So in that case, there's no room for skepticism on anyone's behalf anymore. Our beliefs will converge to the truth, to the same thing. And that is about as far as we can go in answering Hume's problem. In its hardcore form, it's still unanswerable, but we've seen that one can give a partial answer under certain simplifications, like true chances making these coin flips independent, so our degrees of belief converge to the same thing, and that the chance of heads doesn't change from flip to flip. These were all things we talked about last week, of course. So that partial answer is this. We might not be able to predict the next coin flip with certainty, but we can all believe that we'll learn the true chances in the long run. And the true chances are just about as much as you can ask for. Okay, so with that, we'll conclude. I hope this has convinced some people that scientific induction is not a lost cause and that probability theory has a lot to offer in the way of dealing with some of the problems of induction that we've met in this course. Now, since there is no next time, have a go at your self-reflection questions and good luck on the final.